Okay, so Unit 4 is all about these things called integrals. And integrals can also go by the name of antiderivatives, and that kind of hints to what they actually are. It's basically the opposite of derivatives, so derivatives backwards. So like how you have plus minus, or multiply divide, or the exponents and square roots, how those are all opposites of one another. This is the same in calculus. We have derivatives and integrals. Them in themselves are opposites. Integrals have a tiny bit more stuff to them, but we'll get to that later in the lesson, unit, whatever. So what we're going to do is we're going to start to see how we get what we call our reverse power rule. We're just going to go through some stuff to see how we figure that out. So basically what we're going to do, let's just start with 2x. What would we need to differentiate to get 2x? And then if you remember, it would be x squared. If we take the derivative of x squared, we will get 2x. And this applies to a few other things, so let's do another one. Let's do take the antiderivative, as it's called, of 3x squared. So what would we need to differentiate to get 3x squared? In this case, it would be x cubed. So let's do another one. What would we need to differentiate to get 4x cubed? If you're starting to see a pattern on the right side, the answer will be x to the 4th. So let's do something a little bit different. What if we wanted to get negative x to the negative 2? What would we have to differentiate to get negative x to the negative 2 power? And in this case, it would be x to the power of negative 1. This is a bit weird to see. You would basically, that's the same as 1 over x. If you had 1 over x in the form of x to the negative 1, remember taking your derivative, you drop the power to the front, so negative x, and then you have to subtract 1 from the power. So it would be negative 2. And that's how those are the same. And so if you're starting to see a pattern with it, I'm going to show you what the formula is now. Basically, we're going to take the power and we're going to add 1. So this is basically an x to the 1 right here. X to the 1 plus 1 is 2. X to the 2 plus 1 is 3. X to the 3 plus 1 is 4. X to the negative 2 plus 1 is negative 1. So basically, if we were trying to take the antiderivative of x to the n, then our antiderivative would be x to the n plus 1, but there's still a little more to it, and in this case, that reason is going to be because of these constants out front. So basically what we're doing is this same power that we have over here, once we actually take the antiderivative, we're dividing by it. So here it would be x squared over 2. The reason we don't write the over 2 is because we have this 2 out front as a constant already. So basically this is saying 2 times x squared over 2, and these two 2's cancel. So if we were trying to take the antiderivative of just, just the antiderivative of x, this is where we would get x squared over 2, because we don't have a constant out front. So finishing our formula over here, take the antiderivative of x to the n, we get x to the n plus 1 over n plus 1. But there is one condition that this does not work, and that is going to be when x equals negative 1. And so let's try to go through it when x equals negative 1, and we can find out what's wrong. So let's say we have x to the negative 1. We want to take the antiderivative. We plug it into this equation. So we get x, and then negative 1 plus 1 is 0, over negative 1 plus 1 is 0. And simplifying that, we get 1 over 0. And that's undefined, so we don't like that. We don't want that. So that's why this formula always works, except for when x equals negative 1. Okay, so we have our formula. If we have x to the n and we take the antiderivative, aka the integral of it, we will get x to the n plus 1 over n plus 1. But right now it just says x to the n equals x to the n plus 1 over n plus 1, and that's not true. So we have to introduce new notation to show how this means we're taking the integral of this to get this answer. And so that notation is going to look like this weird squiggly s thing, and then you have to write a dx at the end. It's really weird how this represents an integral, and like what is that dx thing there for? So this dx thing, we'll get to that in another lesson. The main thing is when you see this integral sign, that means you're going to take the antiderivative. So if we're going to write it in our notation up here, we would write that squiggly s out front, and then we would write that dx all the way in the back. Technically, there should be parentheses here to show this is what we're taking the integral of. You just technically, we don't really have to write that. Mathematicians are lazy. We don't really write the parentheses, but know that those are there, and that is being, all of this inside the integral is being multiplied by the dx. So just remember that. Okay, there is one modification we have to make to our formula, and And I'm going to show you how that works now. So first, let's say we just want to take the derivative of x squared. We did that earlier. Take the derivative of x squared, you get 2x. But now let's say we want to take the derivative of x squared plus 1. If we take the derivative of this, we're going to get 2x again. And now let's say we want to do another thing. Let's try to take the derivative of x squared plus 30. If we take the derivative of x squared plus 30, we're again going to get 2x. So let's say like earlier, we said if we take the integral of 2x, that we were going to get x squared. But that's not our only answer. The integral of 2x, yes, x squared is an answer, but this is also 2x and this is also 2x. But we have all these functions we can derive to get 2x. So that means we're going to have to make an altercation to our actual formula. And the way we're going to do this is on that side where we, after the integral, like what it's equal to, we're going to write a plus c at the end. A c standing for a constant. Because any constant you derive, you get 0. That's how this stuff works. We derive our x squared, and we get 2x. That's where this part comes from. But if we derive, there's no constant here, so there's not going to get anything. Here we derive 1, that's going to be 0, because deriving a constant is 0. And here if we derive 30, deriving a constant is 0. So all these constants just go away. So at the end of every integral like this that we solve, we're going to write a plus c at the end to just represent all the different constants that there can actually be. Later on in the lesson, we're actually going to learn how to solve for this constant, but for right now, we don't have to worry. If you see an integral, just take the antiderivative and write plus c at the end. So if we were going to apply that to our formula up here, the integral of x to the n dx will actually equal x to the n plus 1 over n plus 1 plus c. And that's it. Okay, so with that, I'm going to show you a few more of our integral formulas. And you pretty much know them already, as long as you know your derivatives, because it's just derivatives backwards. But I'll go through and show them to you just anyways, whatever. So the first one is kind of a sub-formula of this one, or the next few will be, actually. It's just to show you some special cases. So the first one will be the integral of 0 dx. And the integral of 0 is, don't say 0. 0 is technically a correct answer, but it's not just 0. The integral of 0 is going to be c, which is a constant. Because as we discovered when we were getting our plus c in our normal integral formula, we know that if we derive c, which is a constant, we'll get 0. So that means the integral of 0 is going to be a constant. And this is the next one of our formulas. The next one we're going to talk about is the integral of dx. And integral of dx is basically saying the integral of 1 dx. And here, the way we could think of this is instead of the integral of 1 dx, let's think of this as the integral of x to the 0 power. And then if it's the integral of x to the 0 power, we can apply this idea, and this will just give us x. And remember, we have to have our plus c. So that means the integral of dx, or the integral of 1, if you see it like that, is going to equal x plus c. That's our next formula. Okay, so these next few formulas are going to be very similar to formulas we've seen with limits and formulas we've seen with derivatives. It's basically the same across all three of these. So the first one is going to be the integral of a times f of x dx, where a is going to be a constant. And as long as a is a constant, we can rewrite this as a times the integral of f of x. So we're basically just pulling the constant out of that integral. And that is our next formula. Okay, so our next formula is going to be the integral of f of x plus minus g of x dx. And this can be rewritten as the integral of f of x dx plus minus the integral of g of x dx. That handwriting there, but I think you get, I hope you get the point from me saying it. So basically this one's just saying that if you have, if you're adding or subtracting two functions inside of an integral, you could split it into multiple integrals, adding and subtracting the same thing. All right, there's 6 more integral formulas I'm going to show you right now, and I think that the fact that there's 6, you could figure out what they are. These are going to be the trig ones. So we're going to start with the integral of sine x dx, and we're also going to do the integral of cosine x dx, because these are both very similar. So if we integrate sine x, we're actually going to get negative cosine x plus c. And then if we integrate cosine x, we will get positive sine x plus c. Now this is kind of backwards in terms of signs, how the derivatives or how the derivatives of these work. So here's a simple way to remember the derivatives and integrals of sines and cosines. So we have sine, cosine, negative cosine. If you remember this list in this order, it's easy. Because if you go down the list this way, this is your derivatives. And if you go up the list, then this is your integrals. If you already get to the bottom list and do it again, you just skip back to the top. So deriving sine, you get cosine. Deriving cosine, you get negative sine, blah, 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 so on. And if we do it backwards, integrate negative cosine, you get negative sine. Integrate negative sine, you get cosine, so on, so on. So this is a way to remember the sine and cosine integrals and derivatives. Now moving on to our next pair of these trig ones. We have the integral of secant x tangent x and the integral of secant squared x. Now, these are not just like integral of tangent, integral of secant. We're not just going to do the trig functions. All we're focusing on today is these antiderivatives that we recognize. So if we integrate secant x tangent x, if you remember what we have to derive to get this, it will be secant x. And then have our plus c. So if we derive this, we get here. And then if we remember what we have to derive to get secant squared x, it will be tangent x. So the integral of secant squared x will be tangent x plus c. And that is these two. All right, these last two, there's a bit of a sign difference, kind of like how there was with sine and cosine, but it's still very similar. So if we integrate cosecant x cotangent x, we are going to get negative cosecant x plus c. So if you remember, if we derive just cosecant x on its own, we will get negative cosecant x cotangent x. But because it's a positive in the integral, we have to remember that negative when we're actually, when we answer the integral. And likewise, this applies to the integral of cosecant squared x. Normally, what we would do is we would derive cotangent x, and we would get negative cosecant squared x. But because this is a positive in the integral, we have to make our negative over here in the answer to the integral. So the integral of cosecant squared x will be negative cotangent x plus c. With that being said, that's all the integral formulas we're going to learn today. And there's not enough room to write them all on the board, so I'm just going to leave them off, and we're going to go through a few examples before we move on to learning how to solve for the c in our integral. So the first integral we have here is an integral of 1 over x to the 7th plus 5x. And so what we can do here is first what we want to do is realize that we don't have a formula for when x is in the denominator. However, we can rewrite this. So this integral can be rewritten as the integral of x to the negative 7 plus 5x dx. And remember our formula before where we say the integral of f of x plus g of x is the same as the integral of f of x plus the integral of g of x? So we just integrate this term by term and it will be fine. So if we integrate x to the negative 7, we are going to be using that reverse power rule we derived at the start of this lesson. And so we could rewrite this after taking the integral. So the integral of x to the negative 7 will give us x to the negative 6 over negative 6. Remember, if we have x to the n, it will turn into x to the n plus 1 over n plus 1. So that's where this comes from. And we can do the same thing with this 5x over here. So integral of 5x will give us 5 times x squared over 2. And then you can't forget, we have to write plus c at the end. And then that is our answer for this example. Next example we have here is the integral of x multiplied by the quantity x squared plus 3. And so we don't have a reverse kind of product rule kind of thing, whatever. We don't have a way to do a product rule for integration. So because of that, we're just going to have to distribute this x into these terms. So if we distribute x into x squared, we'll get x cubed. If we distribute x into 3, we'll get plus 3x. Don't forget your dx. And then now we can just integrate this just like we did the last one. This will give us x to the 4th over 4, and then plus 3x squared over 2. Don't forget your plus c, and that is your answer. Next one we have here is the integral of the 5th root of x cubed. And this one might look a little scary, but it's actually not bad. All we have to do is turn this from radical form into exponent form. So remember, if we have the 5th root of x cubed, this can be rewritten as x to the 3 over 5. And then so if we follow that same formula, we are going to get x to the 8 over 5 all over 8 over 5. But we're going to have to simplify this a little more because we don't like having this fraction in the denominator. So x to the 8 over 8 over 5 is the same thing as saying 5 over 8 multiplied by x to the 8 over 5. And now that we're done simplifying, this is when we could write our plus c. You could technically write a plus c up here and then keep moving down, but it's kind of annoying just having to rewrite plus c over and over. So all you really need to do is do all your integration, simplify, and then you write your plus c and write it when you're finished at the end. Next up, we have the integral of secant x, all multiplied by the quantity tangent x plus secant x. And here again, we don't have a product rule for integration, so you're going to have to distribute this in here and then solve from there. So distributing secant x into tangent x, we'll just get secant x tangent x, and then plus secant x times secant x will give us secant squared x dx. And then now we can do it term by term like normal. Integral of secant x tangent x will just give us secant x, and then add the integral of secant squared x, which will just be tangent of x. And then your plus c, and that is that one. And then last but not least, before we move on to the second half of the lesson, we have the integral of x squared plus 2x minus 3 all over x to the fourth. And now there's two ways you can do this. One way is which is the way I like to do, is you could split this up into multiple fractions. So x squared over x to the fourth plus 2x over x to the fourth minus 3 over x to the fourth dx. And then you could simplify and do this term by term. Another way people like to do this one is they also like to instead move this as this x to the negative 4. They move that to the, I can't English. They take this x to the 4, they move it into the numerator, and it turns into x to the negative 4. So that would be x to the negative 4 multiplied by x squared plus 2x minus 3. And then you distribute that in, and you basically get the same answer as if you do it this method. This is just the way I prefer it. You could do whichever one fits you best. I'm going to continue with it this way. So simplifying this, we will get 1 over x squared, which can be rewritten as x to the negative 2. This term will give us 2 over x cubed, which is the same as 2x to the negative 3. And this one is just 3 over x to the fourth, as it is. So we can rewrite that as 3x to the negative 4. And then your dx. And now integrating it term by term, we will get a negative, or we don't need our integral sign anymore because we're already integrating. If we integrate negative 2, we will get x to the negative 1 over negative 1. And if we integrate 2x to the negative 3, we'll get 2 times x to the negative 2 over negative 2. And then minus 3. Over here, if we integrate x to the negative 4, we'll get x to the negative 3 over negative 3. So now simplifying this can give us negative 1 over x. And then these 2's cancel. So we will have minus 1 over x squared. And these negative 3's cancel. So we have plus 1 over x cubed. Now that we're done simplifying, we can write our plus c, and this is our answer. Okay, so I'm going to show you a little bit of notation that I probably won't use in these videos, but it might come up sometime, so I'm just going to let you know about it. Say we have f double prime x. We integrate that, we will get f prime x. But what if we want to integrate that? Then we will get f of x. But what if we integrate f of x? F of x is typically as far back as we go, but you can go one level back from f of x. And if you integrate normal f of x, we're going to get what we call big f of x, and it's just a capital F. I don't know what you call it if you integrate big f of x. I don't even know if that's a thing. Maybe it's a giant F. I don't know. But this integrate f of x, you get a capital F of x. That is something you might see. Just be aware of that for the future. Okay, so this next part of the lesson, we are going to be learning to find what's called a particular solution. And now, this is technically the short name. The long name is a particular solution to a differential equation. But what's a differential equation? And that's going to be like this. A differential equation is going to be an equation that involves a derivative and then whatever the derivative is equal to. So on the left-hand side of this table, we have differential equations. On the right side, we have their solution. So a differential equation could be f prime x equals 7. And the answer to that differential equation is going to be f of x is equal to 7x plus c. Another differential equation could be y prime equals 4x. The answer to that differential equation is y equals 2x squared plus c. Lastly, the last kind of notation you see is dy dx equals 15x squared. The solution to that would be y equals 5x to the fourth plus c. Now the only issue with this is all of these solutions are called the general solution. And the reason for that is because they all have a plus c. The c could mean anything, so it's a whole general solution. It represents all the things c could be. Now, if we try to find what c is equal to, that is called a particular solution. I'm going to show you how to do that now. So when you're actually solving for your particular solution, you'll be given a function, or you're not a function, you're going to be given your differential equation. In this case, it's g prime of x equals 6x squared. That looks wrong. That looked like a 7. 6x squared, this is what it is. And you'll also be given a point. Depending on the context, it might be written in a word problem, it might just be straight up given to you, but you'll always be given at least 1 point. And from that, what we do is we take our general solution, and then we can use this point to find the particular solution. I'll show you how to do that now. So first, as I said, you find the general solution. So we're going to have to integrate both sides of this. So that will be the integral of g prime of x. Don't forget you have to write dx, or else it's technically wrong. And then on the other side, we will have the integral of 6x squared dx. And then if we actually integrate this, we will get g of x equals, on the right side, if we integrate 6x squared, we will get, we will get 2x cubed plus c. Now, from here, when we have our actual solved differential equation, g of x equals 2x cubed plus c, we can plug in this point up here. So g of 0 equals -1. So for g of x, we plug in -1. And then for every value of x, we plug in 0. So 2 multiplied by 0 cubed plus c. And from here, the only variable is c, so we can solve for c. 0 cubed is 0, times 2 is 0. So on the right-hand side, we just have c. And on the left-hand side, it is still -1. So we know c equals -1. Because of this, we can plug that back into our original equation, or not right here. We'll plug it in back to the original equation, which is up here, and then we'll actually get our answer. So that would be g of x equals 2x cubed minus 1. And that is our particular solution to this equation. Another example of this concept would be our differential equation is f prime x equals secant squared x, and our point is f of 2 pi equals pi over 2. Now to do this, we do the same thing. Integrate both sides, so integral of f prime x will equal the integral of secant squared x. If we integrate f prime, we will just get f of x. On the right side, integrating secant squared x, we will get tangent x plus c. Now we could plug in our point here. On the right-hand side, or left-hand side, I should say, we will get pi over 2. And then for every value of x, we will plug in 2 pi. So we have tangent of 2 pi plus c. If you remember tangent of 2 pi, that is just going to give us 0. So 0 plus c equals pi over 2. That's the same as saying pi over 2 equals c. So if we plug in our c value back to our original equation, we will get that f of x is equal to tangent of x plus pi over 2. And that is our particular solution. Now a similar but still different thing we might see is we're given a second derivative differential equation, and we are given 2 different points over here. One is from our first derivative, and one is from our actual function. So to do this, it's the same way, we just do it twice. So we're first going to integrate both sides. So integrating f double prime x is going to be equal to integrating all of this stuff over here. So if we integrate f double prime x, we are just going to get f prime of x, and that is going to be equal to the integral of all this. And all of this is just going to be a reverse power rule again. So integrating -2 will give us -2x. Integrating 12x will give us 12x squared over 2, which is the same thing as 6x squared. Integrating -12x squared will give us -12 times x cubed over 3, which is the same thing as minus 4x cubed. And don't forget, we have to have our plus c. And now from here, with our plus c, we are going to take our first point and plug this into our equation to solve for that c. So we will get -12 is equal to -2 times 0, plus 6 times 0 squared, minus 4 times 0 cubed, plus c. All of these terms are going to go bye-bye, because they are all involving 0 and multiplying and stuff. So you'll just get that c equals -12. We can now plug that back into our original f prime. So that means that f prime of x will equal -2x plus 6x squared and minus 4x cubed. And then we have to subtract 12 because c equals -12. And now we just do the same thing again. We're going to integrate both sides of this equation and proceed from there. So integrating f prime of x, we are going to get f of x. And I'm going to switch markers real quick. This one's starting to die. Well, all the markers are starting to die, but so let's keep going. Integrating f prime of x, we are going to get f of x. Integrating negative 2x, we will get negative x squared. Integrate 6x squared, we will get 2x cubed. Integrate negative 4x cubed, we will get minus x to the fourth. And integrating negative 12, we will get negative 12x. And don't forget our plus c, but there is a notation thing we have to do here. Because there is a second plus c, and we already have a value for what c is up here, we can't just call this plus c. What we do is we call it plus c and then do a subscript of a 1 to show that it's a different value, a different c. Even though it's still constant, it's a different constant. So plus c1. And now we are going to use our second point given here to solve for that c1. So plugging in f of 0 equals 4, we will get 4 equals negative 0 squared plus 2 times 0 cubed minus 0 to the fourth minus 12 times 0 plus c1. And again, all of these things with multiplying by 0 go bye-bye. So we just get 4 equals c1. Plug that back into our original f of x. We get f of x equals negative x squared plus 2x cubed minus x to the fourth minus 12x and plus 4. And that is our particular solution for f of x. And don't forget, we had our particular solution for f prime x. It is right here. I just wrote the integral signs in the way, but it's right here. We know our particular solution for f prime and f of x. Okay, we got one more problem for today, and then I'll show you a thing you guys might have a question on, and then we'll be done. So, we have our differential equation and our point, so let's just proceed as we normally do. And integrate both sides. So the integral of f double prime is going to equal the integral of 4 minus, and I know it says 6 over x to the fourth, but I'm going to write it as 6x to the negative fourth, because we can't integrate when that x to the fourth is in the denominator, so we'll just rewrite it in the numerator with that negative sign. Now we can proceed. Integrating f double prime, we'll get f of x, and that will equal, integral of 4 is 4x, and remember, if we are integrating this kind of power thing, we use the reverse power rule, so minus 6 times x to the negative 3 over negative 3. Now I have our plus c. And we can simplify this, negative 6 divided by negative 3, that is just going to equal positive 2. So this is going to say 4x plus 2x to the negative 3 plus c. We can now plug in our first point into here, and we will get 9 equals 4 times 2 plus 2 times 2 to the negative 3. Remember, or not remember, but notice in this case, we're going to have to actually do some work to solve for c, because it's not like all these cancel like before. So we'll have 9 equals 8 plus 2 over 2 to the third. And 2 to the third is just going to be 8. 2 divided by 8 is going to give us 1 over 4. 8 is the same thing as 32 over 4. 32 plus 1 is going to give us 35. So 35 over 4 plus c is equal to 9. And then now we could rewrite 9 as 36 over 4. Subtract 35 over 4 from both sides. And we'll get that 1/4 equals c. That was a lot of by hand work. I'm pretty sure with a lot of these differential equations, you can solve it with your calculator. So that'll go a lot faster, but in this lesson, I don't have that luxury. So yeah, c equals 1/4. I'll erase all this extra work so we can save whiteboard space. But c equals 1/4. And that will mean that our particular solution for f prime x will be 4x plus 2x to the negative 3 plus 1/4. Now we can proceed. Again, integrate f prime x will equal integrating all of this stuff over here on the right side. Don't want to say it because there's so much. And then now if we actually integrate this, we will get f of x equals, if we integrate 4x, we will get 4x squared over 2 plus integrating 2x to the negative 3 will be 2x to the negative 2 over negative 2. And integrating 1/4 will just be 1/4 x. Don't forget we will have a plus c1 this time. I'm going to simplify this a bit before we actually plug in our point. So that will be 2x squared minus x to the negative 2, and then plus 1/4 x plus c1. You can now plug in this stuff back into here. And luckily we have an f of 0 equals something. And that means that this term will cancel. So that just means we'll be given c1 equals 4. Plugging that back in, we'll have our particular solution for f of x will equal 2x squared minus 1 over x squared plus 1 over 4x and then plus 4. This minus 1 over x squared is just the same thing as this minus x to the negative 2. I just turned it back to our normal form for our final answer. But yeah, that's it. Now I'm going to answer a small question you guys might have. So if we had f prime x equals 2x and we wanted to solve for just our general solution, I guess, we'll integrate both sides and we'll get that f of x equals x squared plus c. But some of you guys might be wondering, why did I only write a plus c on the right side? Why did I not do on the left side? Why is that not equal to f of x plus c? And you guys have a valid point. That is correct. Now, one thing, this is not just plus c. Because there's two c values here, one of them would have to be plus c1, as I showed you the reasoning of before. And so yeah, there would be a c and a c1 here. But here's why I don't write it. Because all we would do is we would subtract c1 from both sides. So we would have f of x equals x squared plus c minus c1. But because c and c1 are both constants, we could rewrite it as a new constant. So that would be f of x equals x squared plus c2. And that is basically the same thing as we have up here. It's just a constant with a different subscript label. So why even go through the effort? Why bother? We just say there's 1 plus c on the right side. So even though there's technically a plus c on both sides, we don't have to write it. And that's the reasoning why. And that pretty much wraps up today's lesson. We'll see you in 4.2.